So in today's video, we're going to go ahead and take a look at how we can actually determine global or absolute maximum values or minimum values for a function. And we're going to look at two examples, one of which is over a certain interval of the real line, while the other one is going to be asking about the global maximum over all real numbers for our function, right? And so let's go ahead and actually do that. And we're going to come to find, we previously actually took a look at a couple of examples of how we may graphically interpret the notion of global maximum or global minimum. And now we're going to come to find that the process of actually determining absolute extrema is very similar to the process of relative extrema. And so over here in our first example, we have f of x, which is this polynomial function. And essentially, we're just going to be asked to find the absolute extrema of our function over this interval. So from -1 is less than or equal to x, which is less than or equal to +1, right? And so let's go ahead and actually do that. So the first step would obviously be to take the derivative of our function, because we're just going to use the first derivative test like we did previously, right? And so f prime of x in this case is going to be 6x squared plus 6x. And if you don't know how I found that derivative, then I encourage you to review the video on the power rule. And so essentially now what we need to do is we need to first of all find the stationary points or the critical points of our function. And so we know that this function f prime of x is going to be defined for all real values, right? Because this is going to be defined for all x is a member of R. And that's because of the fact that this is just a polynomial function, right? But now we need to check if it's ever going to be equal to 0. So we can check if this thing is equal to 0, and what we can do is we can divide by 6, right? So we end up with x squared plus x equals to 0. We can factor out our x, and so we get x times x plus 1 equals to 0. And so this tells us that x is either equal to 0 or -1. And so these right over here, these would be our stationary points, right? Or stationary values, if you'd like. And so now that we have our stationary points, what we can do is we need to actually test the nature of these critical points or these stationary points. And so the way I like to do that is by using a number line. So we can do a small number line over here. I don't know why that came out slightly slanted. Let me fix that. So, okay, that should be better. So here we mark our critical points. We have -1. Here we have 0, right? And this is our number line. And what we're going to do is we're going to just see the sign of f prime of x over these different intervals. So for values less than -1, for values between -1 and 0, and for values greater than 0. And so let's go ahead and actually do that. So first, let's take for values that are less than -1, so for this interval. And so we can try maybe f prime of -2, which if we're going to look over here, that's going to be -2 times -2 plus 1, which is -1, so it's going to be equal to +2. So we know that over this entire interval, f prime of x is going to be positive, so we can use a little positive sign over there. We can do the same thing for values between -1 and 0, and so we can choose, for example, f prime of maybe -0.5. And we don't really care about the value over here, we just want to know the sign, and so we're going to have -0.5 times -0.5 plus 1, which is +0.5, and so this value is going to be, what, -0.25? And so we're going to be negative over this interval, or f prime of x is going to be negative over this interval. And then finally, for values greater than 0, the easiest one is probably just 1, so we can do f prime of +1, which would be 1 times 2, which is equal to 2, which is a positive value, so we're going to be positive over this interval. And so now that we have the signs of f prime of x over these different intervals and between the critical values, what we can do is we can actually check, or we can actually determine the maximum and minimum values using f of x, right? So we know that when f prime of x is positive, then f of x is going to be increasing. When f prime of x is negative, then we're going to be decreasing, or that f of x is going to be decreasing. And then when it's positive, we're increasing again. And so we know that at -1, we're going to have a relative maximum, right? Because we're increasing, we reach our critical value where we're stationary, and then we start decreasing again. So we're going to have a relative maximum, if you recall from the first derivative test, at x equals -1. And if we look at x equals 0, we're decreasing until we reach x equals 0, where we have a horizontal tangent or a stationary point, and then we're going to start increasing again, so we have a relative minimum at x equals 0. Now we need to determine whether we actually have a global minimum or global maximum at these points. And so first of all, let's think a little bit about it. Right over here, let's first of all test the endpoints of our intervals. So we know f of -1 is one of our endpoints. And if we were to input this into our function, we'd get -2 plus 3 plus 1, which is what? +2, if I'm not mistaken. Right, 3 minus 2 plus 1, yeah. And then f of +1, that's the other endpoint, right? So we're going to get 2 plus 3 plus 1, which is equal to 6. And so we know that at our endpoints of the interval, we're at 2 and we're at 6. Now let's go ahead and test the value at our critical points, or test the value of the function at our critical points. And so one of our critical points is actually x equals -1. And we already know that we have the point -1, 2 as one of our relative maximum points. But we immediately know that this is not going to be a global maximum point. And how do we know that? Well, it's because of the other endpoint. When we look at f of 1, here we have f of 1 equals to 6, right? So we have another point, which is 1, 6. And we know that this is going to be the global maximum right over here. So this will be the global maximum, right? Because what happens over here is that we're increasing. We reach this relative maximum at x equals -1. We start decreasing again, and then when we reach 0, we begin to increase. And as we increase, we reach the endpoint of our interval. And at the endpoint of our interval, we attain our global maximum. And so we know that we have global maximum at the point 1, 6. And so we know that this point right over here is not our global maximum. So this is not the global maximum, right? Now, what about the global minimum? Is that actually going to happen at x equals 0? Do we attain our global minimum at x equals 0? Well, let's think about it. Let's go ahead and evaluate f of 0, right? And so f of 0 is going to be equal to +1. And so this point would be 0, 1. And if we're thinking about the endpoints, we have the point -1, 2, and then when we reach -1, 2, we continue to decrease until we reach 0, 1, and then we begin to increase again. So we know that this is going to be our global maximum, our global minimum rather. So this is our global minimum because we have, at the endpoints, we don't have any values that are lower, and we know that we keep decreasing until we reach this point, and then we continue to increase afterwards. So there's no way for this to not be our global minimum value. And so that's how we can actually determine global maximums and global minimums over a certain interval. Now let's go ahead and take a look at this other example over here, which is given this function f of x equals the natural log of x over x, for x is a member of real, or x is a real number. And so essentially we're testing this for not necessarily a particular interval of the real line, but the entire real line. And so let's go ahead and do that. So first of all, we can find f prime of x, which is going to be, what, 1 over x times x, which is +1, minus the derivative of the denominator times the numerator. So 1 minus the natural log of x over x squared. I don't know why that didn't become a nice line. Okay, over x squared. Again, if you don't know how I got that result, then I encourage you to review the quotient rule. And so now what we need to do is we need to see where we have critical points at which our function f is defined. And so we can first of all set this equal to 0. And if we're to solve for x, we get 1 minus the natural log of x equals 0. And then we get that the natural log of x equals 1. And so x is going to be equal to e as one of our critical values, right? Let's take a look at some of the other options. We need to see where our function is undefined, and we are undefined at x equals 0. So here we are undefined. F prime is undefined, actually. But then what about our actual function? F is also undefined. So we know that f prime is undefined, but so is f at this particular point. And so we know that x equals 0 is not a candidate for our global maximum or our global minimum, or our global extrema, I should say. So our only point that we have to take a look at is x equals e. So this is the only critical point that we're considering, right? Because it's the only point at which our function and its derivative are defined, and the derivative is equal to 0. And so let's actually go ahead and test the nature of this critical point. So we can use a number line, right? And we can mark e right over here, x equals e. And we just need to test two intervals over here. So the values that are less than e and the values that are greater than e. And so let's go ahead and do the values that are less than e first. So we can take f prime of, for example, 0. It's probably the easiest one. Actually, no, it's not, because 0 is undefined. So let's take f prime of 1. And we get 1 minus the natural log of 1 over 1, which is going to be equal to 1 minus 0 over 1, so it's just positive 1. So we know that we're going to be positive over this interval. And then we can go ahead and take a look at f prime of any number greater than e. We can take e squared, for example, f prime of e squared, which is going to be 1 minus the natural log of e squared over e to the fourth, which is just 1 minus 2 over e to the fourth, which is negative 1 over e to the fourth. And so we know that we're going to be negative over this interval. And so that tells us that f is going to be increasing for all values that are less than e, and then when we reach e, we're going to start decreasing, or f is going to start decreasing as the derivative goes from positive to negative. And so that tells us that we're going to have a relative maximum at x equals e, right? And so do we have a relative minimum? Well, it appears not, right? Because it seems as though we only have an interval over which we're increasing, and then we start to decrease afterwards. And so it appears as though we only have a relative maximum at x equals z. And is this going to be our global maximum? Well, it's the only point at which we kind of attain any sort of maximum. And so because of that, and because of the fact that we're not confined to a certain interval, we can say that this is going to be our global maximum, right? And we can input this into the function if you would like. We can input this into f, so we can get f of e, which is the natural log of e over e, which is going to be 1 over e. And so we have the point e, comma 1 over e as our global maximum.